Dear students, good afternoon. Welcome to our next lecture in fluid mechanics. Today we'll be talking about potential flow. Just quickly checking if video and audio is okay. I tested it before. If you cannot hear me, please make yourself known. Another question is Kai around? Kai, could you quickly
Yes,
get online? Okay, perfect. So today we'll be talking potential flow, and this is a completely new topic. It's very much different from what we talked about the last 2 or 3 weeks. And let me get started on that. Today's lecture is actually the first lecture of a series of 2 lectures, because the whole potential flow theory is quite large, and it deserves 2 lectures to tell you, well, probably not everything, but at least the most important things of potential flow theory that you need to know. Once we're done with that, we actually have roughly 90%, 95% of the framework that we need to know. After potential flow, we will be talking about turbulence, we'll be talking about aerodynamics, which is very much an application of all the topics that we have talked about before. Okay, but for today, we'll be talking about potential flow theory only. Only, that means I need to go back to what we talked about last week just for 1 minute. You remember, or hopefully remember, that last week we talked about boundary layer theory. So boundary layers are something that are close to, well, obviously boundaries, as the name says, so close to walls, or as we see it here in this schematic drawing, close to the surface of an airfoil. It's a phenomenon that we find in, let's say, moderately high Reynolds number flows, so very high Reynolds number flows, but definitely not in Stokes flow. Right? Stokes flow was a separate story, very, very high viscosity compared to inertial effect, so very low Reynolds number. Today and last week, we're in the regime of higher Reynolds numbers, meaning we're starting at Reynolds numbers of 100, going up to thousands, millions, billions, or maybe even more. Now, I just said the boundary layer is this thin layer, maybe a few millimeters or centimeters on a typical wing surface, where viscosity plays a major role. And I'm not sure if I've mentioned this explicitly. If not, I'll do it now. Inside boundary layers, we have relatively high levels of vorticity. You remember vorticity is this quantity which describes the flow field in terms of its rotation. It's in a rotation. In this old movie, we had these vorticity meters that rotated or did not rotate, right? We saw there are different flows. And the boundary layer is a flow where you have a lot of vorticity inside. Actually, one says that walls are vorticity generators. Now, all of this is confined in this rather thin boundary layer. Outside this boundary layer, we have what we called last week the outer flow, the free stream flow. And this flow, this outer flow solution, is the main topic of today. And if we look at the vorticity of this flow, or if we were to test this like in a wind tunnel or water tank, we would find that there's hardly any vorticity, or actually, ideally speaking, there's no vorticity at all in this outer flow. So all the vorticity is confined in the boundary layer flow, and outside we have zero vorticity. For practical sense, we can just say it's zero vorticity. Having zero vorticity, and we'll see this in a few minutes, has a bunch of implications which allow us to solve for this flow in a different way. We don't have to solve the Navier-Stokes equations. It helps a lot, and we can define what is called a potential, and I will explain this in a few minutes on the blackboard, what that means. We can define a potential for this flow. We can only define a potential because this flow has no vorticity. So potential flow, potential does not work inside the boundary layer where you have vorticity, it only works outside where you have no vorticity. Okay. So once we're done with that, we have a solution for the outer flow, the potential flow solution, and we have a boundary layer solution, and we can put the two together, and then we have more or less the whole flow field, in that case around an airfoil. So let us compare the original flow, classical high Reynolds number flow on the right-hand side of this slide, with the thin boundary layer and the outer rotational flow, to what we will focus on today. Today, we'll just forget about this boundary layer and just assume that we can allow for a slip velocity on the surface of the wall. So we're not enforcing the no slip boundary condition on the wall. So we're not enforcing zero velocity on the wall. We just enforce a tangential velocity on the surface of the airfoil. You see underlined, in both cases, we have no through flow through the wall, right? There's no wall, no velocity going perpendicular to the wall, right? Then it would not be a wall. But in the viscous flow, in the boundary layer, we have zero velocity at the wall. And in the irrotational ideal flow, in the potential flow solution today, we have a slip. So it is like a flow without any viscosity, which does make a lot of sense if we have a flow with very high Reynolds numbers. And maybe you remember we had the same picture as that one here last week. And I asked the question, if we cross through the viscous term, 1 over Reynolds times Laplace u, whether this is really a good idea. And I told you last week, it's not a good idea for boundary layers where we want to enforce the no slip boundary condition. Today, we forget about the boundary layer. We have done this last week, and we're just interested in the outer solution. So we can accept that. We can actually get rid of this viscous term, which reduces the partial differential equation, Navier-Stokes equation, to an equation which is only first order in space, has only first order derivatives in space, such that we can only satisfy one boundary condition and not the no slip boundary condition at the wall. These equations actually have a name. They're called Euler equations. And I just want to quickly write it down on the blackboard in a shorthand notation so that you see what equations we actually will try to solve. Let me stop the slide here. So the continuity equation still remains the same as always. It's still the continuity equation. The momentum balance looks like that on the left-hand side with the material derivative. I'm not writing it out with a nonlinear term, I'm just writing this shorthand notation with the capital D, equal to minus pressure gradient. And then there would be the viscous term, but this time we're forgetting about the viscous term. So that's all that we have to solve if we neglect the viscous term for high Reynolds number flows, and if we accept that we do not want to satisfy the no slip boundary condition on the surface, because we have already done this with the boundary layers. And these are the Euler equations. Now, unfortunately, the Euler equations are not really that much simpler to solve. We still have here, with the substantial derivative, a nonlinear term inside, right? This u times a gradient of u. And this nonlinear term really makes it difficult to solve these equations. So it looks like, although we made a simplification to the Navier-Stokes, although we reduced the order in space from second order to first order, not that much has changed and will not be that much simpler to solve these equations. The good thing is, with the potential that I will define, I think 2 slides from now, we will be well off and we can solve these equations really, really simply. You will be surprised how easy that will go. But let me just to strengthen the concept of this potential flow, let's just summarize what we're actually now doing. This was just the introduction. Now let's look at what this ideal flow or potential flow is actually good for. So ideal flow is a synonymous term for potential flow. You will find both things in books. Ideal flow is applicable to flows that are perfectly inviscid, right, where viscosity goes to 0. Or they're applicable to irrotational flows, so no vorticity, like what we have outside of a boundary layer. Even though the fluid itself is viscous, we have an outer flow which has no vorticity. We already talked about this, boundary conditions. We cannot satisfy no slip. And on the right-hand side, let us memorize that ideal flow or potential flow theory is not applicable to Stokes flow because their viscosity is so dominant that it will have vorticity everywhere. It's usually, in most cases, not applicable to interior flows. Why? Because the walls are usually very close and there's no real outer flow. There's no flow far away from the wall. In a pipe flow, like where you have a Poiseuille profile, we derived this 3 weeks ago, essentially everything is a boundary layer. You can think of a Poiseuille flow as 2 boundary layers from either side of the wall that match in the middle. Obviously, we cannot use potential flow or ideal flow theory for boundary layers. We cannot use it for highly rotational flows. Wakes, that's something we'll talk about in 2 weeks when we look at aerodynamics. Sports ball aerodynamics, for instance, where you have wakes downstream of an object. We can definitely not use it for turbulent flows also because they have a lot of vorticity. And that's something we might, well, probably will get there by the end of today's lecture. We cannot use it for drag computation. Potential flow theory, as beautiful as it is, it's completely useless for drag predictions. For that, we need the boundary. Okay, so let's get started. Let's get started with the theory of potential flow or the theory of ideal flow, if you wish. So the first assumption we have to make is that the flow field, and here today we'll just be working in 2 dimensions, but things also work in 3 dimensions, but it's just easier on a blackboard to work in 2 dimensions. We have to assume that our flow field, our Eulerian flow field consisting of a velocity u and a velocity v, can also be described by a so-called potential. A potential at the end of the day is just a function. It's a function of x and y, and it's a scalar function. So it's not a vector like a velocity vector, it's just a scalar, it has a number in it. So for any position in the flow field x and y, it has a number in it. And the potential, and that's why it's called a potential, has the property that the gradient of this potential phi is the typical variable we use, the gradient of this potential phi is equal to a velocity u. So what does that mean? Let me draw a little picture on the blackboard just to get this idea straight. Stop here. So let us assume that we have a coordinate system x and y. And on this x and y coordinate system or flow field, we have a potential function defined phi of x and y. Now we can draw so-called isolines, right? Lines where the function, the potential function has the same values, right? So for instance, like that, and so on, huh? So these are all lines. On each one of these lines, the potential function has a certain constant value, like phi 1. Huh? Let's say on this line, we have the value phi 2, and so on. So what is the gradient? I hope you can see these lines there on screen. Use a different color. So what is the gradient of such a function? The gradient has the property that the gradient is always perpendicular to one of these isosurfaces. So just think of this as a map, and the potential function would be like the elevation. This would be like a hill. The gradient is always pointing towards the path of steepest descent downhill, right? So for instance, if you were standing at this point, the gradient points in this direction. Or at this point, the gradient points in this direction, or in this direction, or in this direction. Okay, and we have now defined that the potential is made such that the gradient of the potential is equal to velocity vector. So that means this here will be a velocity vector. Or this here will be a velocity vector. Or this here will be a velocity vector, right? So once you have a gradient, a potential flow function, potential phi of x and y, you can compute the velocity vectors at any place you want just by taking the potential, the gradient, sorry. Written out, what does this mean? U and V here are d phi dx and d phi d1. That's the definition of the gradient. Okay, so that's already quite cool. Maybe you don't really get what this has to do with no vorticity and why this is so useful. Let me go back to the slide now. Well, what does this have to do with vorticity? Well, vorticity is actually a prerequisite or a necessary condition, necessary and sufficient condition that a potential exists. Because it's not really obvious that for any flow field that could exist, that there is such a potential function. Potentials only exist, potential functions only exist for flow fields that have zero vorticity. And I can show you this again on the blackboard, why that must be the case. Let me move over to wipe out part of that. Let us assume now, let us assume that we do have a potential function. Let us compute the vorticity. So the vorticity omega is defined as the curl of the velocity vector u, right? That's how vorticity was defined. I think it was in the second lecture of this course. So what does this mean? This means, maybe rotate my camera a little bit. What does it mean? The curl of u in 2 dimensions is simply dv dx minus du dy. Okay? So far, I just used our definition of the vorticity. Now, assuming that we do have a potential, we can replace the v and the u in here by the potential itself. So we can also write the vorticity omega is equal to dv dx, and this is now d dx of, and v is d phi dy, okay, minus d dy of u, and u is d phi dx. And look at these terms, 2 terms now. d dx, d dy of phi minus d dy, d dx of phi. And we know that differentiations can be exchanged, right? They're linear functions. So these 2 terms are equal. So that means the vorticity is 0. So what does that mean? If a potential exists, the vorticity automatically is 0. There's no other way. And you can do the same derivation or same argument also backward and saying only if the vorticity is 0, there will exist a relation like that. The relation like that is equivalent. Let me write it up here. This is really equivalent to the statement that vorticity is 0. Okay. And this is why this whole concept of potential flow only works in a vorticity-free, or as people say, in an irrotational flow field. Okay, so I have now hopefully been able to make the connection why irrotational flows and potential are related, have to be related, why one doesn't go without the other. I have not yet explained to you why it's useful to have a potential. I mean, so far, we just created a new variable and some more math and some more equations. Now, the usefulness of the potential comes into play when we go back to our Euler equations, to our simplified Navier-Stokes equations. These are the equations we would actually like to solve. Let's see if we can use these equations together with our definition for the potential to come up with a new equation, with a useful equation, which tells us how to compute this potential, right? It would be beautiful if we had a simple equation that tells us how to compute or what the potential needs to satisfy. If any one of you sees where we can use, I need to move up a little bit, where we can use this definition in here. Well, as always, it's best to start off with the continuity equation. Let me write down, maybe I use, let's move over the other side of the blackboard. Let me write down the continuity equation again. The continuity equation on mass balance says the divergence of U must be 0. So the divergence of, and we know that U can be described by potential. Divergence of the gradient of phi must be 0. Right? So just use our definition of the potential and plug it in. So what is this? Let's write it out. So the gradient, that's d dx d dy, right? This is this gradient operator, scalar product with this. That's the gradient of phi. So that's d phi dx, d phi dy, right? Just written out these two terms here. So scalar product means we multiply the first component with the first component, or we apply the first component to the other first component. So that's a d square dx square. So a second derivative with respect to x plus the second component applied to the other second component plus d phi dy squared. And I hope you all recognize what this is. This is just simply the Laplacian of phi. Okay, and that's also something you will find in any book on vector calculus, that the divergence of a gradient is the same as the Laplace. Okay, so just by simply satisfying or trying to satisfy the continuity equation by applying our definition for the potential, we were able to come up with a rather simple fundamental equation for the potential. A potential has to satisfy a Laplace equation. Right? So Laplace equation is the equation we have to solve. We don't have to solve, go back here to the right-hand side, we don't have to solve the Euler equations for irrotational flows. It's fully sufficient to satisfy this very fundamental, very canonical Laplace equation. The solution of the Laplace equation is the potential, the flow potential. And once we have the potential, we can easily compute the velocity field just by taking the gradient. Of course, that's not the complete story. Solving a Laplace equation, I mean, the Laplace equation has many solutions, actually, infinitely many solutions. Of course, we have to solve it for the appropriate boundary conditions. To understand what these boundary conditions are, it's actually worthwhile, again, to draw a little bit of a picture down here. Let me do an object here. We have a more or less blunt body, and we have a flow, an oncoming flow from the left streamlines which roughly look like that. Now let us try to think what the potential must look like. You remember from the picture I drew here on the right-hand side, I talked about potential lines. We drew them in yellow. So these were equipotential lines. Yellow lines were lines with where the potential has a constant value. And we saw that these lines are always perpendicular to the velocity vectors. So we can actually think of the opposite. If we know the velocity vectors or the streamlines here, we know that the equipotential lines must be perpendicular to it, right? So they must be perpendicular to any point on the streamline, like that, right? On any point of the streamline, the equipotential lines must be perpendicular. So they will look something like that. Okay. So these are lines where the potential phi has a constant value. And these lines are perpendicular at any place to any streamline. They're always perpendicular. What does that mean on the surface of our object? Well, remember this time, we're not talking about boundary layers. So we're allowing non-zero velocities on the surface, but we're not allowing any velocity going through the surface. So what does that mean? That means that the surface of the object itself must also be a streamline. Probably there's one streamline coming here, this going out like that. And because equipotential lines are perpendicular to the surface, to the streamline, they must also be perpendicular to the surface. And these are boundary conditions. We have to find solutions for the Laplace equation for which equipotential lines are exactly perpendicular to the surface. Or, let me now use a different color. surfaces are in vector geometry. It's a nice way to define a surface by its normal vector, right? If you know the normal vector, you know the direction of the surface. And you can say that the velocity at any point on the surface must be exactly perpendicular to the normal vector. So our boundary condition, mathematically speaking, I hope I have enough space. Maybe let me wipe out that part here to have a bit more space. On the surface, the velocity u must be perpendicular. Sorry, this is an n here, n, and this is a u, huh? So u scalar product with n must be 0. This is our boundary condition. Huh? At the wall, this must be satisfied. And if we translate u in terms of the potential, we can say gradient of phi is the velocity times the normal vector for the wall must be 0. Okay. So these are our boundary conditions. And together with the Laplace equation, this fully defines the problem. And this has unique solutions, well, unique up to a constant actually, has unique solutions for the potential. Okay. Let me switch back to the slides. Okay, so what have we done on the blackboard? We have seen the velocity potential exists if and only if the flow is a rotational. That's what we did over here. We computed the vorticity, and so the vorticity always has to be 0 if there is a potential. And we have shown here, up here, that satisfying the continuity equation is tantamount to satisfying a Laplace equation for the potential. Maybe some of you, when they saw at least the first 2 lines of this slide, remembered what we did with the stream function, right? In the second lecture, flow kinematics, we introduced the so-called stream function. It had almost the same Greek variable. Instead of phi, we had a psi. And instead of these relations, we had relations which, well, were not exactly the same, but looked similar. Huh? We actually had v equals minus d phi dx and u equals plus d phi dy. But still, it was very similar. So there must be a duality, and there actually is, and that should be shown on this slide, on the next slide. There's a duality between the stream function and the potential. See here again the 2 definitions, how stream function psi and velocity potential phi are related to the velocities u. You see it's like flipped and one has a minus sign. Otherwise, they're the same. Now remember, we had the equipotential lines. That's what we just did on the blackboard in yellow. And we had the streamlines. And we know that streamlines are actually lines for psi constants. So it's like streamlines or iso stream function lines. And streamlines are perpendicular to potential lines. So what this means, let's go back to this picture. The blue lines, the streamlines, are actually lines where psi is constant. And the yellow lines are lines where phi is constant. So the two functions, phi, potential, and psi, stream function, they both describe a flow field, just in a different way. Their isolines are perpendicular. Isolines of the stream function are streamlines, which are perpendicular to isolines of the potential. And that's what they look like. Okay. This is a nice, beautiful duality. And there's even more to it. Maybe you've seen it on the slide. There's a similar function, or actually the same equation for the stream function. And I'll show you how to derive that. The last thing we do, and then I think we're going to take a break. Move up. Down maybe. So what do we know of the stream function? See how far that goes. Okay. So just for us to remember, a stream function is defined such that u equals d psi dy, and v is minus d psi dx. Now again, let us compute the vorticity of a flow field by using the stream function. So the vorticity of a flow field is dv dx minus du dy. And now we do as before, we replace the v by the expression for the stream function, and we do the same for the u. So we have a d dx of v is now a minus d psi dx minus d dy of u, and u is now d psi dy. Okay, so the vorticity of a flow field can be written as minus, this is 2 times d dx. So it's a second derivative with respect to x. And we pull the minus sign out, and this is a second derivative with respect to y. And this, of course, just minus the Laplacian of psi. Okay, so we have not yet done anything with potential flow. So far, we just wrote the vorticity, let me write this here, vorticity omega can be written in terms of a stream function as minus the Laplacian of the stream function. You can do this whether it's potential flow or anything. You can always do this with any stream function. Now, if it's a stream function that is related to potential flow, we know that the vorticity is 0. So we can say that for irrotational flow, so for flow where omega is 0, which happens to be a potential flow or an ideal flow, we have omega equals minus Laplace of psi equals 0. Okay. So under the condition that we're looking at irrotational flow, there is also a Laplace equation for psi. So we have Laplace equations for phi, Laplace equations for psi. Of course, the boundary conditions are different, right? There, the velocity vector, or well, the velocity vector has still to be perpendicular, but there the streamlines are parallel to the wall. For potential flow, we had the equipotential flow perpendicular to the surface. For the stream function, the streamlines must be parallel to the surface. That's the only difference in a boundary condition. The equation looked the same. Okay, so we're actually almost done. Let me just go back to the slide and summarize. We have a Laplace function also for the stream function. We have slightly different or perpendicular boundary conditions. At the same time, there's a lot of duality between these two equations. And actually next week, we're going to show that these can be treated in one function. You can use a complex function formulation where one is the complex part and one is the real part of the function. But that's for next week. For now, we just accept that both have a lot of similarities and both can be computed from the same type of equations. Okay, so I think it's a good point to take a little break here. Let me just check the next slide. Yes, well, actually, we can look at this quickly. These are just Laplacian operators standing in the boxed equation for cylindrical coordinates. And this is really nothing for you to learn by heart. It's really just for reference. So we're going to take a break now, and next hour, second hour, we're going to look at solutions, at actual solutions of this. Okay, so let us meet again at a 1/4 past, and then we'll continue. Thank you. Dear students, welcome back to the second part of today's lecture. So last hour we introduced a new function, a potential function, and we saw that it is a solution, or it can describe a flow field as long as this flow field has no vorticity in it, or as we say, it is an irrotational flow field. We also found a duality with the stream function that we know already for 4 weeks, 5 weeks now, I think. And we saw that both have to satisfy a so-called Laplace equation. Now, Laplace equations are, as I said, they're very fundamental canonical equations. They appear in many, many places in physics. And it's also something that can be solved quite well on a computer. So there are many computational fluid dynamics codes which are based or actually making use of this potential flow theory, they you can give them like a shape of an object, for instance, an airfoil, and they will compute for you the streamlines around it by solving the Laplace equation. But we're not going to do that. I'm going to show you an alternative way of finding solutions. And that way of finding solutions has a lot to do with one of the basic properties of such an equation. Let me write down the Laplace equation again for the potential. So we have Laplace phi equals 0, which is of course much simpler than the original Euler equation or even Navier-Stokes equation that we had at the beginning of this hour. Now, one of the fundamental properties of this equation is that it's a linear equation. Linear equation means that if we have multiple solutions that satisfy this equation, the sum of two of these solutions are also solutions of the equation, right? It's a linear superposition of solutions. So if we find a bunch of possible solutions, we can start adding them up, combining them, and by default, the combination of multiple solutions will still be a solution because it's a linear equation. And that's the idea of the method of fundamental solutions. We're trying to find some fundamental solutions of Laplace. In the first place, we're not bothering yet about the boundary conditions. We just look at some very prototypical, if you want, you can call them prototypes of solutions. And then we piece them together, add them up as we like, such that one resulting streamline matches the surface of our body. But you'll see this in examples. So let's look at some of these fundamental solutions. Let's look at the slides here. So the solutions we're going to look at in the beginning, or the next 40 minutes, 30 minutes, is a solution of parallel flow. Maybe a bit boring, but it's the most fundamental one. We're going to look at the stagnation point flow, which is rather complex, but still surprisingly simple. We're going to look at an ideal vortex. Maybe you remember that term, ideal vortex. We had this, I think, even in the second week when we looked at a vortex without vorticity, right? That was the ideal vortex, no vorticity in it. That pops up again. We're going to look at the source and the sink, and we're going to look at the dipole. All these fundamental solutions satisfy the Laplace equation. Therefore, superpositions, sums, combinations of multiple of these fundamental solutions will still be solutions of Laplace. So let's get started with the first one. Let me come back to to the blackboard. So this is the second derivative, and the second derivative of a function must be 0. Sorry, I just need to switch off something on my screen. So what if phi was a constant? What if phi was a constant? What is the second derivative of a constant? Well, it's 0, right? So obviously, a constant is a possible solution. What if phi was a linear function, like a function, say, a times x plus b times y? If you take a second derivative of such a function, it will also be 0, right? let's try to use polynomials, or well, actually you call them monomials, right? Monomial functions. So 0th order is phi just a constant. Now that is a solution of the Laplace equation. And we know that u is the gradient of phi, but the gradient of a constant is also 0. So the velocity field it describes is 0. Okay, so mathematically, mathematicians probably would say, yes, this is a solution. It has a flow field. For us, for practical purposes, it's not very useful, right? So any phi constant describes a 0 flow field. It also means that any solution, we can always add a constant to it. It will not modify the flow field. Let's go to first order solution. So phi would be, for instance, u times x. U is now a constant. You will see in a second why I'm using the word, the variable u. U times x plus v times y. Could also be a times x plus b times y. The gradient of phi is, well, the gradient is d phi dx. D phi dx is just u. This one is 0. So d phi dx is u. And the second component is d phi dy. D phi dy of that is 0. And here is just a d. So this potential is a solution to the Laplace equation because the first order monomial, and it describes a parallel flow, right? It's a parallel flow with components u and v, right? Just streamlines that go just parallel in one direction. The corresponding stream function just looks like that, minus vx plus uy. And you can easily see when you look at the definition how psi relates to the velocities u and v, that it describes the same flow. So we'll describe a flow field with streamlines that are just parallel. You have the components capital U and capital V, and the equipotential lines are just perpendicular to it. Huh? So this is maybe the simplest potential flow solution we can have. Let's go to yet higher order. Let me just propose something. Propose it with some hindsight. Second order polynomial phi equals, just pick my notes, a times x squared minus y squared. The quadratic function, if you take the second derivative of that, it's not zero, right? It's a non-zero, so it's the second derivative d phi dx squared and the second derivative with respect to y. They're both not constants, not zero identically. Let's take the second derivative. This is 2ax for the first derivative. The second one is 2a plus, now the same with respect to y, 2ay, and again derivative, so it's minus 2a. So that satisfies the Laplace equation. So we know that is a potential function. And we can compute the velocities coming out of that. So what are the velocities? U is equal to gradient of phi. So the gradient of phi is 2ax and the second component is dy of phi, so that is minus 2ay. So these are the velocities, u and v. Let's see if we can understand what this is. Let me draw a diagram here. Use the blue. So what are the velocities on the y-axis? On the y-axis, the coordinate x is equal to 0. So on the y-axis, this is always 0. So we have a negative velocity vector pointing downward. Starting here, going down. And the higher up we are, the larger it becomes. So far up here, you have a large velocity going down. And the closer we get to the origin, the shorter velocity vectors become. And here at the origin, the velocity is exactly 0. On the x-axis, maybe I draw this blue anyway, sorry. Farther away, the higher the velocities, the closer, smaller velocities are the higher. That's 0. And on the x-axis, it's the same thing except with a positive sign. We have rather small velocities that increase the farther away we go from the origin. And if we continue doing that, we'll see that we have velocities or streamlines which actually look like that. We have velocities which are high, far away, go down, get slower and slower toward the origin, and then accelerate again as we go out. What do the equipotential lines look like? And they must be perpendicular to the streamlines. Here, this is exactly a 45-degree diagonal. And here, they actually go perpendicularly to the x-axis. And because the x-axis and the y-axis are both streamlines, they could also be a wall, right? We can consider this to be a wall. So the flow field we have just drawn, the flow field that is described by this potential function, is actually the solution for the flow in a corner, the flow in a rectangular corner. Apart, in reality, we'll have a little boundary layer here because we need no slip, but outside the boundary layer, which will be confined to the wall, this is a very accurate, very precise solution for flow field. Okay, so you hopefully start seeing the beauty of this. These are already quite complicated flows, and we could just write them down. And well, 2 or 3 lines on the blackboard, we have solutions for these flows. So this flow is not only the solution to a rectangular corner. If you look at the equation, where did I drop my blue chalk here? Well, this also, this is not just a solution in this part of the xy plane, it's also a solution for negative x. So the same story also works over here, right? And we can also assume, or not assume, we can also say that this potential flow here is not only a solution for the flow in a corner, it's also the flow, a solution for a flow impinging on a flat plate. This is a wall here, and we have flow coming from above, impinging, like a jet impinging, and then it separates, goes out left and right. Simple as that. It's called stagnation point flow. Why stagnation point flow? Well, because here, let me use a different color, because here we do have a stagnation point. Here the velocity goes locally 2 to 0. That's the stagnation point. That's why this is called stagnation point flow. Of course, stagnation point flow, or corner flow if you like, it has next to the potential has also the corresponding stream function, which just looks like that, 2a x y. And you can easily check yourself that these two are absolutely corresponding. Both satisfy the Laplace equation, their own Laplace equation, and both describe the same velocity field described. Okay, that's quite nice. What else can we do? So we have filled this blackboard. Parallel flow on the left, stagnation point flow. Maybe let me write that down. So, stagnation point Or equivalently, if you just consider this half here, it's a corner flow. Stagnation point flow. Oops, I already spilled it. The next thing I want to talk to you about is a vortex. That's the ideal vortex. We had the ideal vortex in the second week, where we showed that there's a vortex without vorticity, and because it has no vorticity, it is also flow that has a potential solution to it. There exists a potential which describes this flow. And I hope you remember that in this flow, obviously it was spinning, right? So the circles you see on this slide are streamlines, so it has circular streamlines. But that the velocity was decaying like 1 over r, r being the radius. The farther away we go from the radius, the more the velocity decays. If you go infinitely far away, you have a zero velocity. If you go to the center, you have a singularity actually. So actually, mathematically speaking, the center of this flow is not an exact flow, or it's not a solution. So let me write down what the potential function of this flow actually is. Start with the second blackboard. And we're going to move over against the other side. So I can tell you that the potential phi equals to yes, I think that was a gamma. Gamma, I'll tell you what the gamma is, just a factor, it's just the strength of the vortex times arc tangent of x over y is a solution to a Laplace equation. Maybe not so obvious, but you can go up and look in your books or use Mathematica to take the Laplacian of this function. You see Laplacian is exactly 0 of this function. Now, it's actually worthwhile to translate this not in the xy coordinate system, or not look at this in the xy coordinate system, but actually to translate this. Now what is actually gamma over 2 pi. Sorry, this is what I have wrong before. To go into polar coordinates. So far, we always look at the coordinates x, y, but because now we will have circular streamlines. If I can draw a nice circle here, almost. So we have circular streamlines. It's actually worthwhile to go into a coordinate system with a radial coordinate r and then azimuthal angle theta. And if you look at what arctang x over y actually is, arctang x over y is nothing but this angle, or I have it gamma. Is just equal to gamma, equal to arc tang x over y. Just basic trigonometry. Okay. So this can also be written as gamma times, sorry, theta times gamma over 2 pi. This is actually a much more useful way of writing the potential, because now we can immediately understand what it does. What are equipotential lines? So lines where phi is constant. Well, gamma over 2 pi, these are constants anyway. That's strength of the vortex. So wherever theta is constant, we have an equipotential line. So equipotential lines, we usually do them in yellow. So lines where theta is constant are equipotential lines. So obviously, on a ray like that, phi is constant. Any ray here is an equipotential line. And of course, since streamlines must be perpendicular to equipotential lines, these are then our streamlines here. Yeah? And of course, these lines are lines where our stream function is a constant. And let me just write down what the stream function actually is. The corresponding stream function psi is actually minus gamma over 2 pi. It's again the strength factor times logarithm of r. And it's very clear to see whenever r is a constant, this expression is a constant. So lines of r constant, which are circles, are streamlines. Why log r? Well, you need a log r because only with log r you get it satisfies the Laplace equation. What about u and v? Or let's say, what about the velocities? Let me draw them here. The velocity in the radial direction, ur, and the tangential velocity, u theta. What about these velocities? ur and u theta can actually be computed from the gradient of the potential, but now it's the gradient in polar coordinates. So for that, you need to go back to the slide, I think 3 or 4 slides ago. We're not going to go through that. I'm just going to tell you what the result is. With this stream function, this potential function, ur comes out as identical to 0, which it should be. There's no radial velocity. There's only an azimuthal or tangential velocity. And the tangential velocity is gamma over 2 pi r. And that's exactly what we already knew of this ideal vortex. The velocity with which the vortex is spinning is decaying like 1 over r as we go away from the center. And now it also becomes a bit more clear where this whole gamma over 2 pi comes from. Gamma actually has a name. Gamma is called the circulation. Circulation gamma is a quantity, it's a strength of a vortex. The higher gamma is, the faster such a vortex is spinning. And it's actually defined as an integral along a streamline. So for instance, the integral along one of these blue curves, so once in a circle, of the velocity vector u along this path S, right? In general, you can take any path, but we would just take a path S along one of these streamlines. So we go once around and add up all the velocities along this circle. Let's do that. So for this circle here, with a certain radius r, the velocity here is just gamma over 2 pi r, okay? And if we, because it's constant along the circle, if we integrate it along the circle, we can just multiply the velocity by the circumference of the circle. What is the circumference of a circle? 2 pi r, okay? So the circulation of this vortex is gamma divided by 2 pi r times the length of the circle, which is 2 pi r. So the circulation of this vortex is just gamma. This is why here we have a gamma over 2 pi. This is just written such that whatever we choose for gamma happens to be the circulation of this vortex. Okay, this is how an ideal vortex is defined. And now I would like to play with you a thought experiment to come up with the next fundamental solution that we have. We have talked about the duality between stream function and potential function, and we saw that the equipotential lines must be perpendicular to the streamlines. And the equipotential lines are the yellow lines, and the blue lines are the streamlines. Now let's try to imagine that we flip the roles of the two. Let's think of the blue lines as equipotential lines, and then the yellow lines will be streamlines, right? Both should still satisfy the Laplace equation. So we just exchange the roles of the two. Instead of psi is equal to minus gamma over 2 pi log r, we make psi is equal to gamma, theta over times gamma over 2 pi. We just flip them. What do we obtain? If we flip the two, let's go here. If we do flip two, we obtain streamlines that go out like rays, and we do have corresponding equipotential lines, which are just circles. What is this? This is something like a source. With somewhere in the center, and the center is actually again a singularity, just like in a vortex where the center velocities go to infinity and they're not really a part of the solution. The exact center is a singularity, but outside we just have streamlines going out. Just think of this as a well where water is coming out and it's just spreading out in all directions. So this is a source And the stream function is simply m over 2 pi times gamma, theta. Just the same we had for the potential before is now the stream function. And the potential is what used to be the stream function before, and it's m over 2 pi times log r. Okay. You may see a slight discrepancy. Well, we skipped the minus sign. It's more a matter of definition in which direction the flow is going. And you see that we introduced a new variable. Instead of gamma, which had the role of a circulation, we now have an m. M, again, is the strength. It's the strength of the source. And you can actually, again, do an integral along one of these circles and add up. You add up all the radial velocities going across one of these yellow lines, one of the equipotential lines. And what would you get? You would get the mass flow rate. If you integrate all the velocities going across a certain line, it's like a mass balance. And we know from what we looked at before, the integral along one of these lines will just be m. So m is actually the flow rate. Right? It's the strength of the source. This is how much mass is coming out of this well here in the center. What if m is negative? Well, if m is negative, the flow will go in. So it's not a source anymore. It's then a sink. So for m positive, we have a source. For m negative, we have a sink. That's simple. What else can we do? Imagine you put the source and the sink next to each other. Let me maybe go here. Some space left. Let's put a little keep losing my chalk here. We have a little source here, and we have a little sink here, both of equal strength. So both will cancel out. What flows out and one goes back in the other. And locally, the streamlines will look like that. Here it goes in and here it comes out. But there will be a connection between the two. Okay, so we have two poles. They're also called poles, monopoles, sources and sinks. They're poles. And if we put two poles next to each other of opposite strength, they will cancel each other far, far away, but locally they give a rather complex flow field. If we bring them closer and closer and closer, as we bring them infinitesimally close, we end up with a so-called dipole. Two monopoles coming together infinitesimally close are dipoles, like the one we see here. So this is the stream function of a dipole. Let me go over here. I need to put power on my laptop. Okay, so we have now defined a bunch of different fundamental solutions. We have started with a parallel flow. We have gone over to a stagnation point flow, corner flow, with the second order polynomial, x squared minus y squared. We have introduced the ideal vortex, which we have now seen maybe in almost every lecture we came across this ideal vortex. We have seen sources and sinks, which are like the inverse of the ideal vortex. We just flipped the potentials and the stream function. And finally, we have seen that if we bring two sources and sinks, a pair of source and sink very close together, actually infinitesimally close, we get a dipole solution. Two monopoles give one dipole, which has these streamlines, like circles on the other side. Now, as I said, these are all solutions of the of potential flow, but they're not yet anything. Well, maybe the corner flow is, but all the others are not that useful in practice. I will now show you what you can do with a dipole and the parallel flow. Just imagine you take such a dipole solution, or actually a source and a sink close together, and you add a parallel flow to it from the left. Just think of that for a second. And let's move over to the next slide. This is what the solution will look like. Let me spend a few more minutes before we finish on that, to end up with this application. So let's see what happens if we take a dipole, and the dipole gives us streamlines which look like that. And of course, here in the center, we have actually one single streamline which just goes upstream and one going to the right. And we add to that a parallel flow from the left. For both, we have potentials. This is the sum of a monopole and the sum of a source and a sink, and we just add to that the potential of a stream function. Of a parallel flow. So let's look at the streamline here in the center. Here is the flow coming with velocity u. From that side is dipole velocity coming with a very high velocity in the center, but the farther away we go, the velocity will decay, right? If we go far, far away from the dipole center, the velocity will go to 0. So there will be one point somewhere here where the oncoming velocity u and the velocity from the dipole exactly cancel. They're exactly of equal size, but just opposite direction. So this is where we will get a stagnation point of 0 velocity. And if we play this game a bit more, we will see that we obtain one streamline which looks exactly like that. And all the other streamlines will wrap around this point. Inside, we'll have some distorted circular streamlines. But what is really important is that streamline here in the center. Let me draw it with a different color just to make the point clear. There's one streamline which has this shape here. Huh? And actually, because the dipole is symmetric, it will even close here in the back. Huh? So by simply adding a dipole and the parallel flow, we get a closed body. Huh? And if I draw it a bit more nice, you would even see that it's not just an elliptic body, it's actually a circle. Okay, so let me come back to that, then finish up. Well, this is actually parallel flow with the source here. This is what we get if we add a parallel flow from the left to a dipole. We get one streamline, which happens to be exactly a circle. So let's finish with that picture. We'll look into this a bit more closely beginning of next hour. But the beauty of that is that the two fundamental solutions, parallel flow and dipole, added together, give you a result, the full result of the flow around a cylindrical body, which is a rather complex flow field, but you can write it down in a nice and simple way, and you can even start computing pressures on the surface, but I'll show you all that next week. Okay, so I think for now we can stop, and as I said, we'll look at these final slides again next week, and I think Kai will continue now with the homework assignment, and I would like to close here and say thank you and see you again next week. Bye-bye.